Hi everyone, today's topic is how to reduce conductivity in your water. No matter how you use it, conductivity in water can be a problem. So how do you reduce it? For that matter, what causes conductivity in water? Let's find out. What is water conductivity? The conductivity of water represents its ability to conduct an electric current. It is important to note that in its pure state, water does not conduct electricity. To be a conductor, water must have some cations and anions that will allow the transfer of energy. Knowing this, you can understand that water with a high conductivity is also highly concentrated in total dissolved matter. The unit of measurement used to express the conductivity of a water sample is Siemens per centimeter or microsiemens per centimeter. The expression microsiemens per centimeter can be expressed in ppm to make it easier to understand. In fact, some conductivity meters calculate this automatically. To put things in perspective, a microsiemens represents the electrical conductivity equal to 1 per million of Siemens. The Siemens is a unit of measurement in the international system of units. When expressed in terms of alternating current, the Siemens represents the reciprocal relationship between impedance and ohms. For direct current, the Siemens represents the reciprocal relationship between resistance and ohms. Before going any further, let's remember that the conductivity of water is affected by the type and quantity of ions in the water. Indeed, the type of ion found in a body of water will have an impact on the conductivity since some materials are better conductors than others. As for the quantity, it is logical to think that the more conductors there are, the higher the conductivity. Finally, the temperature of the water will have a proportional impact on its conductivity. Basically, increasing the temperature of the water increases the solubility of the minerals and the mobility of the ions in it. This is the reason why an increase of 1 degree Celsius can represent an increase of 2 to 4% of the conductivity. Water total dissolved solids. Total dissolved solids, TDS, are organic and inorganic contaminants that can be found in water naturally or not. Since they are the source of conductivity, it is important to note that they are both cations and anions. Among the cations most often found in Canadian waters in dissolved form, we find calcium, magnesium, sodium, and potassium. Anions include carbonate, bicarbonate, chloride, sulfate, and nitrate. Briefly, the materials dissolve in water through soil erosion, runoff, or decomposition of flora. Since the covalent bonds of water molecules, H2O, are stronger than the ionic bonds of these contaminants, the water molecule breaks the bonds between them. Once these bonds are broken, the water molecules, which have a special polarity, surround the ions. Is water conductivity hazardous to health? To answer quickly, the answer is no. As stated above, the conductivity of water represents the total dissolved solids concentration in the water. Since TDS generally represents minerals, it is not harmful to human health. On the other hand, water with total dissolved solids is prone to present particular odors, unattractive colors, and particular tastes. Finally, it is important to specify that although in general the consumption of water with any conductivity does not present a health risk, there are obviously exceptions. Continually consuming these contaminants can generate an excess in certain minerals and impact your body in various ways. Moreover, it is recognized that concentrations of total dissolved solids exceeding 1,000 milligrams per liter or 1,000 ppm are not suitable for human consumption. Why is monitoring conductivity important? In general, water conductivity does not pose a hazard to water treatment equipment. However, for some specific uses such as high-pressure boiler water or microprocessor production, conductivity can be problematic and can cause problems for equipment or products. For example, for high-pressure boilers, the presence of total dissolved solids, indirectly from conductivity, can lead to the creation of foam in the boiler. If the boilers provide turbines, the foam can promote the formation of residues on the turbines. This can affect the efficiency and safety of the equipment. Next, it is important to remember that salt water has a high conductivity since salt ions are good conductors. Therefore, if the conductivity of your water is caused by the presence of salt, your equipment can pay the price since the presence of salt can accelerate the corrosion of the systems. How to reduce water conductivity? Knowing that the conductivity of water comes from the ions in it, it is obvious that the extraction of these ions will have an impact on the conductivity. Therefore, in order to achieve a target conductivity, the water must be treated by removing the conductive contaminants in the water. Nanofiltration is a separation technique that works by using a physical barrier or filter to block certain contaminants in the water. Nanofiltration membranes have 0.001 micron pores, which allows these filters to remove bacteria, viruses, minerals, and even some salt ions. Without going into superficial details, nanofiltration requires a physical barrier and pressure to force water through the pores of the membrane to work. Nanofiltration will have an impact on conductivity since it has the ability to extract dissolved materials from the water. Due to their variable size, some ions cannot be extracted by using nanofiltration. This is why typically the use of this technology will allow a reduction of about 50 to 70% of the conductivity of the water. Moreover, depending on the quality of the water you are dealing with, filtration steps may be necessary before nanofiltration since water with too many contaminants will clog the membranes too quickly and reduce the effectiveness of the treatment. Reverse osmosis is probably the most versatile water treatment technology available. The principle of osmosis is very similar to that of nanofiltration. The difference is the type of membrane used to separate the contaminants. In a simplified way, the difference between reverse osmosis and nanofiltration is the size of the pores. Indeed, the pores found on osmotic membranes have a size of 0.0001 microns. When reverse osmosis is used for conductivity reduction, the principle is the same as that of nanofiltration, to extract dissolved matter from the water. In contrast to nanofiltration, reverse osmosis allows the extraction of approximately 90 to 95% of the conductivity in the water. To achieve 95% conductivity removal, double reverse osmosis may be required. Again, unless the feed water is particularly pure, reverse osmosis cannot usually be used alone or the membranes will foul too quickly. Typically, the concentration limit for total dissolved solids in water to be treated by RO is 70,000 ppm. When the TDS concentration is higher than 70 ppm, the osmosis membranes will clog up much too quickly. To achieve a higher extraction rate than that offered by reverse osmosis, it is necessary to use polishing techniques, which are technologies installed downstream of an osmosis to extract the recalcitrant residues in the water. Operating on the principle of ion exchange, electrodeionization is a polishing technique that works by producing a continuous electric current to continuously regenerate a resin bed. When water comes in contact with this current, it breaks down to form one H-positive molecule and one OH-negative molecule. These molecules are responsible for the regeneration of the anionic and cationic resin in the EDI module. The principle of ionic exchange remains the same. The contaminating ions are exchanged for ions, allowing the production of pure water. When contaminated water passes through the resin bed of an electrodeionization module, the H-positive and OH-negative ions on the resin are exchanged for the contaminant ions in the water, producing ionically pure water. In order to help you identify an optimal solution for your needs, we will present three situations. In the first situation, the water needs will be less than 20 GPM. The second will be for needs between 20 and 500 GPM, and the third will be for needs over 500 GPM. In each of these situations, two water qualities are presented: less than 50 microsiemens per centimeter and less than 5 microsiemens per centimeter. For the production of 20 GPM or less of water with a conductivity of less than 50 microsiemens per centimeter, reverse osmosis is generally suggested. As for the pre-filtration required for your osmosis, this will vary depending on your feed water and will not be covered in this video. If you require higher quality water, the best option is to add a resin bed ion exchanger. In this situation, there are two options for this type of technology. You can have a complete separate bed ion exchanger system installed, or, if you have a service provider nearby, you can opt for a DI service option. These services usually consist of tank rental, and resin regeneration. The advantage is that you don't have to worry about managing the risk of storing the hazardous materials used for regeneration, and the associated costs are generally advantageous given the small amount of water required for your operations. In short, whether you opt for the complete installation of a system or the DI service option, these two technologies together will allow the production of water with a conductivity of less than 5 microsiemens per centimeter. Again here, for the production of water with a conductivity of less than 50 microsiemens per centimeter, the use of reverse osmosis alone would be ideal. However, for the production of water with less conductivity at this flow rate, the resin bed ion exchanger would not provide. Therefore, a combination of reverse osmosis plus EDI should be chosen. By adopting electrodeionization, the conductivity of the water will be below 5 microsiemens per centimeter. Although the initial financial investment will be higher, the long-term profitability will be much more profitable and due to the low operating costs of the EDI modules. For the production of 500 GPM of water and more, it is always the same principle. For a conductivity of less than 50 microsiemens per centimeter, reverse osmosis alone is still the best choice. On the other hand, for water production of less than 5 microsiemens per centimeter, we go back to resin bed ion exchangers. However, in this situation, the installation of a complete system with separate bed resins and regenerators will be necessary since the equipment becomes too massive to be transported economically. As you may have noticed, these suggestions do not include the nanofiltration mentioned above. This is because nanofiltration offers essentially the same type of treatment as reverse osmosis, but in a less efficient manner. This technology could be prioritized when the targeted conductivity is between 50 and 100 microsiemens per centimeter. TDS and conductivity, a history of the past. Let's recall that the conductivity of water is caused by the presence of dissolved matter in it since pure water does not conduct electricity. The technologies allowing a reduction of the conductivity are very varied. We have presented the most common and effective ones. No matter what your water production goal is, achieving it is not a problem. What can be challenging is identifying the best solution for your needs. Selecting the wrong technology will not prevent you from lowering the conductivity of the water. However, the cost and profitability of your equipment will be greatly affected. Anyway, we hope you have found answers to your questions in this video. If you have further questions, we invite you to contact us. Our water specialists at DurPro will be happy to answer all of your questions and needs.